Alrighty, so quick video. This is going to cover questions, well, all the questions on today's worksheet. Today is Tuesday, so the day before the test. I'm going to quickly talk about the ideal gas law, and then we're going to get into those questions. So remember that the ideal gas law tells us about the relationship between pressure, volume, amount of gas, and the temperature. We saw from doing a little bit of data analysis that if you take the pressure of a gas sample and multiply it by the volume, then divide it by the product of the number of moles times the temperature in Kelvin, we always get the same number. We always get 0.0821, and then our unit is this weird compound unit, liters atmospheres per mole Kelvin. Now this compound unit is kind of difficult to really conceptualize what that means. But like I said in class, that is okay. We don't really need to have a good grasp on what this unit is, but we do need to know how to use it, and we need to know that this unit is important. So remember, I showed you that this number has a name. This is called the gas constant, and it is symbolized by the letter R. Yes, I know G would make more sense, but unfortunately G was taken. So this happens in science a lot when we have to define constants. We can't use the letter that makes the most sense for various reasons. So rewriting it a little bit, we can say that P times V divided by N times T is equal to R, and then that can be rearranged into a more familiar PV equals nRT. You can see to get from here to here, all we're doing is multiplying both sides by NT. When we multiply both sides by NT, it cancels from my left and it moves over to my right. So we are left with PV equals RNT, and then for some reason that is commonly rearranged further to nRT rather than RNT for no reason. I don't know why nRT is the most common way to see that written. It doesn't matter, of course, because we know that no matter what order you multiply in, you get the same number. So PV equals nRT is the way that you will see the ideal gas law written most often. So that's what this formula is referred to, the ideal gas law. And our ideal gas law can be rearranged to solve for any of the variables that my question is asking for. So let's say, for instance, that my V, N, and T are all given by the problem, but it's asking what is the pressure exerted by this gas at that specific volume when it's that amount of gas at this specific temperature. So what we would do is we would need to rearrange this equation to solve for the missing variable, in this case P. So if we want to get P by itself, we should divide by V. That cancels it on my left, and I'm left with P equals nRT over V. Now I can just plug all my numbers in, plug in the number of moles for my N, the temperature in Kelvin for my T, the volume for my V, and of course my R is always the same. That's my 0.0821. That's a really ugly 8. 0.0821 liters atmospheres per mole Kelvin. So yeah, that's how we use the ideal gas law. In these questions, we have several of these that require us to use the ideal gas law, but some of them don't require the ideal gas law. So this is something that you're going to have to be able to do on the test tomorrow, is look at a question and decide whether a PTVN table is needed or whether the ideal gas law is needed. So I'll show you how to make those decisions. All right, so using this information up here, this is giving us the hint that if we are given 3 of the 4 variables PTVN, it's an ideal gas law question. But if we have something changing, so if it talks about like having an initial set of conditions and then a final set of conditions, that's when we're going to want to use the PTVN table instead. So let's look at question 1 and try to decide what we are using here. If you have an unknown quantity of gas at a pressure of 1.2 atmospheres, a volume of 3,100 milliliters, and a temperature of 87 Celsius, how many moles of gas do we have? So right away, I notice that we only have one set of conditions, and also we are given pressure, volume, and temperature, and we are being asked for moles. So this is an ideal gas law problem. So I don't need to use my PTVN table in this case. So let's get the ideal gas law written down. PV equals nRT. And then in this case, since we are being asked for moles, that's N, I want to get N by itself. So I'm going to divide both sides by R times T. That cancels it from our right side, and we are left with PV over RT equals N. So let me just get those out of the way. Now all that's left to do is to plug in our numbers for my pressure, volume, temperature, and of course our gas constant R. Our pressure, that's easy, that's 1.2 atm atmospheres. My volume is given to me as 3,100 milliliters, but since this is an ideal gas law problem and the value of R is based on the units liters, atmospheres, moles, and Kelvin, if I am given any numbers that are not in these units, I have to first convert to those units in order for this R to be accurate. So even though I'm given it in 3,100 milliliters, I'm going to convert that to 3.1 liters. I need liters because this is an ideal gas law problem. Also, I'm given 87 Celsius. I can't use Celsius. I need that to be in Kelvin because remember, pressure and temperature are only directly proportional if I use the Kelvin temperature scale. So I will convert my temperature from 87 to whatever that is in Kelvin. I don't remember. To convert to Kelvin, we will add 273 to my Celsius temperature. So I'll take 87 plus 273. That is 360 Kelvin. Okay, so let's get the rest of these numbers in here then. 360 Kelvin, that is my temperature. And my R is going to be that 0.0821 liters times atmospheres per mole Kelvin. And now I am free to punch my numbers into my calculator. Okay, 1.2 times 3.1 divided by 0.0281, 360. All right, 0.126 moles or 0.13 moles. I don't really care how you round for this. I could be more particular about that, but whatever. We will leave it like that. Now, if you are having trouble getting that number out of your calculator, I have two things to say to you. First, make sure that you are using parentheses appropriately. I would recommend typing it into your calculator as 1.2 times 3.1 divided by, and then open your parentheses, 0.0821 times 360, close parentheses, equals. That's how I would type it into my calculator. That way you can do it all in one go, and that'll work just fine. If you're still having trouble getting that into your calculator, here's what I can also say to you. If you set it up like this, and you show me your math and how you are, like what you're trying to multiply and divide by, and if you write it down like this, and then you flub your calculator work and you get some other number, I can probably give you most of the credit. All right, because this is not a how to use your calculator class, it's a chemistry class. And if you can get this number, or if you can get this setup, then I am probably going to be mostly okay with it. You probably won't get full credit, but you'll get most of the credit if you're able to set it up. All right, so with that being said, let's move on to question number 2. I want to move through these kind of quickly now so I can get this video up for you as soon as possible. This time we have a sample of gas with a volume of 5.23 cubic centimeters, pressure of 72.6 kPa and a temperature of 298. What will be the volume if the pressure is changed to 124 kPa and the temperature is changed to 273? So for this one, since we have two sets of conditions, you can see we have two temperatures right here. We also have two pressures. This is not going to be an ideal gas law problem. This is one where we need to use the PTVN table. So I will start plugging in my numbers here. We should be pretty good at this by now. So I'm not going to explain every decision that I'm making here. All right, so getting those numbers in there is the easy part, probably. And then the most important part, where you are most likely to make a mistake in my experience, is in this effect row. So let's walk through this slowly the first time, and then I'll go faster in the other problems. I have a pressure increase. Pressure is going up, so I can write P up. And then I'm also going to write what effect that has on the variable that I'm solving for. So since I'm being asked about volume in this particular question, I'm not just going to write P up, but I'm also going to write what effect that has on volume. So P up, V down, of course. And that's it for this box. So let's move on to our temperature effect. We can see that T is also going down from 298 to 273. And again, I want to think about what effect that has on my volume, since my volume is what I am being asked about. So I'm going to decide that my volume is going down because my temperature is decreasing. And now I'm ready to do my math. I can see that both my pressure change and my temperature change are contributing to a volume decrease. So when I do my math, I'm going to start with my 5.23 cubic centimeters. I'm going to multiply by, of course, two ratios. The question here is, how do I set up my ratios? Do I want them to be the bigger number on top or the bigger number on bottom? So for my pressures, since my volume needs to decrease as a result of my pressure change, I'm going to put the smaller number on top. Put the bigger number on top. That would make my 5.23 centimeters, that would make it bigger. I don't want it to get bigger. I want it to get smaller. So I'm going to multiply it by a fraction that is less than 1. The way to make a fraction that's less than 1 is to put the smaller number on top, 72 over 124. My temperature is also making my volume drop, so I'm going to make the same decision over here, 273, the smaller number on top of the bigger number, 298. Now what I want to point out here is that hold on. My initial, I'm going to do in pink real quick. And my final, let's do in orange. What I want to point out to you is that in the first ratio, notice that my initial is on top of my final. But then for the next ratio, my final is on top of my initial. That is allowed. That is okay. I know that some of us are feel like that must be wrong. It is not the case that we always have to put the initial on top, that we always have to put the final on top, or that even both ratios have to agree. The way that I decide which number goes on top is by looking at the effect that those changes have on my volume. So since the pressure change is making my volume go down, I'm going to put the smaller number on top, whether it's the initial or whether it's the final. I'm going to put the smaller number on top. And then same with my temperature. My temperature is making my volume go down, so I'm going to put the smaller number on top, whether it's the initial or whether it's the final. I don't care. I care about which one is smaller. And so once I have this set up on my paper, then I can start punching numbers in my calculator. 5.23 times 72.6 divided by 124 times 273 divided by 298. And I got 2.8 cubic centimeters. Cool. Okay, how many do we have left? 1, 2, 3, 4 left. I'm going to try to get through this a little bit faster from now on, so sorry. Okay, let's talk faster. 6 moles of gas in a container with a volume of 25 liters and a temperature of 220. What is the pressure in the container? This is another example where I'm given 3 of my variables and I'm asked to solve the 4th one, P. So this is an ideal gas law problem. I'll start with my ideal gas law as it's normally written, PV equals nRT. This time I'm solving for P, so I'm going to rearrange this to get P by itself. I can do that by dividing both sides by V. That'll leave me with P is equal to nRT over V. Now I can just plug numbers in. So I can see that N is going to be 6 moles. My R is always the same, 0.0821 liters times atmospheres per mole Kelvin. And my T is 220 Kelvin. Nice, we don't have to convert to Kelvin this time, it's already like that. And I'll put 25 liters on the bottom because that's my volume. That was easy. Let's just plug in our numbers now. 6 times 0.0821 times 220, divide by 25. I get 4.33. That must be the pressure in ATM. Very good. On to 6. At STP, a sample of gas occupies 24.5 milliliters. Calculate the volume of this gas at a pressure of 2.3 atmospheres and a temperature of 301 Kelvin. Okay, what does this STP mean? Maybe you are wondering that. That means standard temperature and pressure. That might be a term that you haven't seen before. I'm sorry about that. But now you know, standard temperature and pressure. Standard temperature and pressure, we might remember from a previous worksheet that standard pressure is 101 kilopascals, which is also equal to 1 ATM, and there's a handful of other units. Since my question here is using 2.3 atmospheres as the second or the final pressure, we'll use 1 ATM as our initial pressure. That is standard pressure for our purposes in this question. Standard temperature is 273 Kelvin. No, you do not need to memorize that. That's okay. If you need to know it for the test, it'll be there on the test for you. So yeah, don't worry about that. We also know that it occupies 24.5 milliliters. I am not going to convert to liters because this is not an ideal gas law problem. If it's not an ideal gas law problem, I can just leave the units in the same units that they're given in, and that's just fine. Now we want to calculate the volume of the gas. So what is the new volume when the pressure is not 1 ATM but 2.3 ATM and the temperature is 301 Kelvin. So that is a pressure increase. When P goes up, I know V goes down. T is going up, that makes V go up. So on one hand I have volume decreasing, and on the other I have volume increasing. That is okay. That is allowed to happen, remember? So I'm going to take my 24.5 milliliters. I'm going to, just like always, I'm going to multiply it by 2 ratios. My first ratio is going to be determined by my pressures. Looking at my pressures, I can see that my pressure change from initial to final is causing my volume to go down. Since my pressure change is making my volume go down, I'm going to arrange my pressures to make this 24.5 smaller. So I'm going to put my 1 on top of my 2.3. This is a fraction that's less than 1, so it will make my my number smaller. If I arranged it the other way, it would have the opposite effect of what I want. Now my temperature, on the other hand, is making my volume go up. So for this one, I'm going to put the 301 Kelvin on top of the 273 Kelvin. Put the bigger number on top this time. And now I can just punch these numbers into my calculator and I'll get the right answer. So let's go 24.5 times 1 times 301 divided by 2.3 divided by 273. I got 11.7. So that is 11.7 milliliters. There's my answer. Going on to 7, we got 2 more. 500 liters of gas in a flexible wall container prepared at 0.95 ATM and 473 Kelvin. So let's get those numbers into my initial, because I can already tell that this is not going to be an ideal gas law problem. So I get 500 liters, 0.95 ATM, 473 Kelvin. Tank cools 295 Kelvin. Pressure of the gas is now 30. So a big pressure increase. We want to know what's the new volume. Don't need my N column. Let's get our effect row in. P is increasing by a lot. That means V is decreasing. Temperature is going down from 473 to 295, so that means V is decreasing. And now I just need to set up my ratios. I'll start with my 500 liters, multiply it by 2 ratios. My first ratio is going to be my pressures. I want this ratio to make my volume smaller, so I will put the smaller number on top, 0.95 over 30. And for my temperatures, I will put my smaller number on top again because my temperature change is also decreasing my volume, 295K over 473K. And now I can punch this in, 500, 0.95, I got 9.9 liters. Fantastic. And let's go number 9. If you had 1.9 moles of gas held at a pressure of 5 ATM, in a container with a volume of 50 liters, what is the temperature of the gas? This is another one where I'm using the ideal gas law. PV equals nRT. I'm solving for temperature this time. If I want to get temperature by itself, I'm going to divide both sides by nR. That cancels it out. So I get T is equal to nR. Let's plug in numbers for PV, N, and R. For my pressure, I got 5 ATM. For my volume, I got 50 liters. Divide that by my number of moles, which is 1.9 moles. And R, of course, is always the same, 0.821. Notice, by the way, that I have written my units on every single number that I've written so far on this sheet. I am expecting you to do the same. So, sorry. Good news is on the quiz you don't have to do like 8 PTVN tables. It's a fair bit shorter than that. But yeah, just keep that in mind. Now I got these numbers in. Let's put them in the calculator. 5 times 50, divide by 1.9, divide by. Sorry, I messed up. 5 times 50. Divided by 1.9, divided by 0.0821, and I got 1603 Kelvin. It's pretty hot. Okay, there we go. There is my video key for you. If you have any questions on this, write them down so that you can ask them tomorrow before the test. Great, thanks for watching.